Okay, so next, I'll try to measure the value of the friction force using a greater mass. First, we had 115.6 grams, and then I'll add another 480.8 grams. So if I increase the mass, which means the normal force is also increasing, so I will have a greater friction force over here. So first we had 20 grams, and then I'll add another 50. It's not moving, so I'll just keep adding. Good morning, everyone.
Good morning.
So I think we're all ready to start today's experiment, which is about friction force. So before we go to our experiment, I think we should start by defining what friction force is. So can you tell me what friction is?
Friction is a force that exists between two surfaces, and it resists the motion between the two surfaces. For example, when I move this block, frictional force exists between the table surface and the bottom surface of the block, thus resisting the motion of the block. When I move this block to the right, frictional force acts to the left. And when I move this block to the left, frictional force acts to the right. So this is why we say frictional force opposes the motion of an object.
Is there friction when the block is at rest on the tabletop?
I think there is no friction unless there is a force causing the surfaces to slide over each other. But the most important question is, why does friction exist all the time? It's bad.
Well, friction exists because most surfaces are not perfectly smooth. For instance, let's take this tabletop. When we look at it through the naked eye, it seems perfectly smooth. However, if we look at it through a very big microscope, we'll be able to identify little bumps on the surface. So when two surfaces try to move past one another, these little bumps collide. So as a result, it will cause friction and slow down the motion. And if the surface is very rough, there will be more bumps on the surface, which means the effect of friction will be high. However, friction is not always bad, as you explained earlier. There are situations in which friction is absolutely necessary.
But as long as I know, friction is the force that makes pulling and pushing of an object difficult. Also, friction causes wearing and tearing of objects, thus causing additional lubrication costs. So where is it good attributes?
The most obvious example of friction is walking. You know, it is very difficult to walk on a smooth ground. If there was no friction between the tires of the car and the road, motion would be even difficult for vehicles. Other examples of frictional forces are very numerous because friction happens at any time when the two surfaces are touching.
Okay, now I see friction is not bad all the time. It's necessary at some time.
Yes, it is necessary evil.
Now we all know what friction is. We know that friction exists between two surfaces, and it always opposes the motion of bodies. Frictional force, when two bodies slide over each other, there is always frictional force opposing the motion of an object. There is no friction unless the two surfaces start moving. But if you try to move an object gently, it might not move. Thus, you need to increase your force in order to move that object. The force resisting you to move that object is what is known as static friction. And static friction is always present before an object starts moving. And at the point when an object starts moving, we call the force limiting friction. So we define limiting friction as the minimum force required to move an object. As we discussed earlier, we saw what static and dynamic friction is. Now we're going to qualitatively demonstrate the work of static and dynamic friction. Let us place this object on the surface. We see that the surface is inclined a little from the horizontal, but yet the object is not moving. This is so because there is a force that exists between the two surfaces and prevent the motion of the object that is sliding in this direction. But as we increase the angle of inclination of the surface, let us see what happens. not moving yet. See? At one point, the object starts sliding. Let us see it again. Yes, it slides. So, at this point, when we increase the angle of inclination, the object starts sliding. This is so because when the angle of inclination increases, the normal force decreases. And the frictional force preventing the object to slide depends on the normal force. So, when the normal force increases, the frictional force increases, causing the object to slide.
Wait, I think you made a mistake. It didn't increase. The normal force decreased, and the friction decreased as a result. So there's no the force that prevented the motion of the object decreased. So that's why we were able to observe the sliding of the object. Yes, so you can proceed.
Thank you. Yes, I made a mistake. So the normal force is the force that presses an object with the surface. When the surface were horizontal, the normal force is maximum. But as theta increases from 0, then the normal force decreases. And the normal force decreases. At 90 degrees, when the surface is at 90 degrees, the normal force becomes 0. So the object slides completely. As a conclusion, from our observation, we know that as theta increases, that is, our angle of inclination increases, the normal force decreases. And at one point, the angle of inclination, that is in our observation, at 32 degrees, as we see in our protractor, the object starts sliding. And this is due to the force of the parallel component of the weight of the force equal to the frictional force. Here, the parallel component of the weight of the force is mg sine theta, while the frictional force is mg cos theta. Mu mg cos theta. So at this point, mu mg sine theta equals to mu mg cos theta, that is, the parallel component equals to the frictional force, and the object starts sliding.
Yes, what you said is correct, but I think you make some error in the formula. The formula for the sliding force that's parallel to the inclined plane is mg sine theta, which is the sliding force, and the friction force is mu mg cos theta. So we can conclude that mg sine theta is equal to mu mg cos theta.
Yes.
Okay, so here we have horizontal surface, and I'll be trying to measure the amount of the limiting friction, and after that the block will be able to move. So first we have 20 grams over here, and the object is not moving, so I will try to add another 20 grams. And as you can see, it's not moving, which means it's not enough, so I will add another 5 grams. And as you can see, it started moving, so we record the value of 45 grams in our graph.
That will be a frictional force.
Yes. Okay, so next, I'll try to measure the value of the friction force using a greater mass. First, we had 115.6 grams, and then I'll add another 480.8 grams. So if I increase the mass, which means the normal force is also increasing, so I will have a greater friction force over here. So first we had 20 grams, and then I'll add another 50. It's not moving, so I'll just keep adding. It's 120, 170, 220. So I think the value for the friction force is 220, so we'll correct that. Okay, so now I will increase the mass again. The mass that I will add is 632.5 grams. Okay, so and we'll try to measure the value of the limiting friction. Okay, so over here I have a mass of 420 grams, but obviously it's not enough to move the object, so I will keep on adding other masses. So first I will add another 20 grams. So 440, still not enough. So I'll add another 20 grams. 160. And then I'll add another 10 grams. So it started moving. So the value is 470. Okay, so we have recorded 3 values. So can you analyze the conclusion of our experiment?
We recorded 2 values, that is the normal force when you increase the mass and the frictional force. So now we're going to calculate the mu by dividing the frictional force by the normal force. Wow, the results are nearly similar.
Yes, in this data, the ratio of the frictional force and the normal force is nearly constant. And this is what we call the coefficient of static friction, which shows the constant of proportionality. So this shows that the ratio of frictional force and the normal force depends mainly on the nature of the material.
So it does not depend on the normal force and the frictional force when they change.
Okay, so now let's summarize the findings of our experiment.
Okay. Firstly, we saw that frictional force is a force that exists between 2 objects. And we also saw that frictional force opposes the motion of the body by acting in the opposite direction of the motion. And in our second experiment, we saw that the frictional force depends on the normal force, and by varying the angle of inclination, we saw that the normal force decreased, and also the frictional force decreased because the frictional force depends on the normal force. And in our last experiment, we saw that the force of friction we obtained and the normal force are proportional, giving us similar values. So this value is what we know as coefficient of static friction, and coefficient of static friction mainly depends on the nature of the material.